All right, let's go through the practice exam. Let me get some of this out of the way. Okay, so I'm just going to go start to finish through all the problems. There are um, a lot of problems on this practice exam. There may or may not be that many on the real exam, but just be prepared for all these types of concepts. All right, so first we have 10 multiple choice questions. That is how the real exam will be as well, and they're kind of more definition or maybe a little less math based generally. So the first one is a kinetics problem, and it's telling me that this was the graph that I found with a straight line. So can I figure out the rate law? So it says in here, the reaction rate is found to depend only upon the concentration of X. So all of these that have Y in them, gone, right? It can't depend on Y. And then this graph is what's going to tell me which of the two that only have X in it is. And the fact that it's a straight line when it's 1 over X tells me it's second order with respect to X, which would be X squared. Remember, if it's natural log of X, that would be first order on the Y-axis versus time. And if it's just the concentration, that'd be 0th order. But if it's 1 over the concentration, that is second order. So that would be B. Okay, this one is a little bit more math-ish, but it says the city's water supply is contaminated with a toxin at a concentration of 0.63 milligrams per liter. Fortunately, this toxin decomposes to a safe mixture of products by first-order kinetics with the rate constant of 0.27 days. How long will it take for half of the toxin to decompose? So half of the toxin to decompose, that's just words that mean half-life, right? And I know how to relate half-life for a first-order reaction to the rate constant. It's the natural log of 2 over the rate constant K. So natural log of 2 on top. Sorry, I've got lights everywhere here, but all right, so natural log of 2, and that's just that 0.693. If you remembered that number, you could type that in instead, divided by 0.27. To 3 sig figs. I rounded it to 3 sig figs. I wrote 2.57, but my answer should only be to 2 sig figs, so that would be the 2.6. This is days, inverse days in the denominator, so that would be the numerator, so A. A cubic unit cell with 4 atoms in it, so remember if it's simple cubic, that would be 1 atom per unit cell. Body-centered cubic would be 2 atoms per unit cell, and then face-centered cubic would be 4. Intermolecular forces for this molecule. Okay, dispersion, yes, absolutely. Remember, everything has dispersion forces. Dipole forces would be if it's polar, or maybe I don't know a lot about organic chemistry. This is all carbons and hydrogens in here, whether I know that or not. I can see there's an NO2 up here and an OH down here. Those aren't going to cancel each other out. So it totally looks polar to me. Yes, it looks like it should have dipole forces. And a hydrogen directly bonded to a nitrogen. Sorry, hydrogen. Yes, directly bonded to, nitrogen, oxygen, or fluorine right there. And so it would have hydrogen bonding as well. So I want to pick E. The solubility of gases in water usually decreases with, and I've got pressure and temperature things. So remember, the solubility of gases in water usually increases with increasing pressure, and so that's not it. And so I've got both options for temperature. So usually we found things are more soluble in cold, gases are more soluble in cold temperatures. So I want the solubility to decrease. That would be increase the temperature. Think about it like a soda, right? More carbon dioxide dissolves when it's cold. So decreasing the temperature would increase the solubility. That's different than a solid. Usually we would heat something up if we want more sugar to dissolve, but for gases it's opposite. All right, so there's page 1. Page 2, the data refers to the following reaction. Find the concentration of Br2 when the system reaches equilibrium. Okay, so they gave me something that kind of looks like an ice table here. I'm going to kind of finish it by making this really the equation at the top and sort of squeezing in a change line here. And so this would be like minus 2x plus x, sorry, minus 2x, minus x, and plus 2x. Change the sign where the arrow changes, which I put the arrows in so I would know where that was, and then I still put it in the wrong place. But anyway, this went down, right? So 0.25 to 2, so I know that one's going negative. That one should be negative, so that one should be positive. What's it actually asking me for? Find the Br2 concentration. So here I can say like 2x equals 0.5, right? This says it should be 2x, but it went down by 0.5. So my x would just, I mean, you might be able to do this in your head without writing out so much as I am, but that's okay. Whatever works for you. I just want to show you lots of ways to do it so you can pick what works best for you. I see that x is then 0.25, so 5 minus 0.25 would be 4.75. All right, for this reaction, delta H is this, delta S is this. Which of these statements is true? And it says they're all about like when is it spontaneous? Spontaneous at high temperatures, at equilibrium at 25, spontaneous at low temperatures, spontaneous at all temperatures, or delta G becomes less favorable as temperature increases. So that's also something about spontaneous. This one would be quite a coincidence. I could figure that out if I narrow it down to none of the others make sense. The one where it says like it is at equilibrium at 25. I mean, that could happen. I would have to do the math to see. But what I'm going to look at is the signs here. This is negative for delta H, so that means it's exothermic. It's giving off heat. That sounds spontaneous. And it's a positive delta S. Disorder is increasing. That also sounds spontaneous. And so this combination of a minus delta H and a plus delta S is when it is always spontaneous. If you're not sure how I'm drawing that conclusion, it's from this equation. If I put a negative in here, I'm definitely going to put a positive in for temperature because it's Kelvin. They're always positive, and then the S is positive. So this is all going to end up being negative, and a negative, it's always going to be negative. Delta G will always be negative. They have this temperature where they switch only if they have the same sign, so if they're both negative or both positive. All right, which of the following aqueous solutions has the highest boiling point? Tells me the Kb. So if I think about this, the molality is the same and the Kb is the same for all of them. But if I look more closely, I see they're all electrolytes. They all have a metal in them. So if I look at my periodic table, I did not print a periodic table for this. Hold on, let me find myself a periodic table. Here we go. All right, here we go. All right, so I've got sodium, I've got potassium, I've got aluminum over here. So all of those are metals. And if I have metals, that's an ionic compound. And so that means I should incorporate the I. So let's figure out what the I is. And it seems like whichever one has the biggest I is going to make the biggest change in boiling point. So this would be 1 aluminum and 3 hydroxides. I equals 4. This would be 1 potassium, 1 chlorine. I equals 2. And this would be 2 sodiums. The polyatomic ion stays together. So 1 sulfate. I equals 3. And then which of these would I expect to have the highest boiling point? These are just substances, not solutions. So I'm thinking about intermolecular forces here. Which ones would have the strongest intermolecular forces? H2, that sounds like it's non-polar. It's the same thing on both sides. So that would have low boiling point. CH4, hopefully you remember that carbon and hydrogen make a non-polar bond. So that would be non-polar. These guys, I could put a little bit more work into figuring out if they're polar or not, but maybe I noticed something special about NH3 here, which is that it has hydrogen bonding. And so it would be the highest. It would have the highest boiling point and it would have the highest melting point. Right? Those are both things that are affected by intermolecular forces. All right, so that's the type of questions I think you can expect. Obviously, there'll be different questions. So prepare for, that level of thought, I guess. All right. Moving moving on. A certain first order reaction A to B is 25% complete in 42 minutes. What is the half-life of the reaction? All right, let me just pause this video and find my equation sheet so I can show you what you'll have available. All right, of course, as soon as I paused it, I found it right away. So you will have the rate laws here. So here's the rate law that I can use to help me with this one. It's a first order reaction. And I can figure out K in this case. Maybe I want to write it a little bit differently so I can move. I want to group the natural log stuff over. And then I can combine these. And when you subtract logs, you just keep the log and divide the things. So this is just another version. If that feels like log stuff you might not remember, it may be worth memorizing this version of it. We do come back to this in chapter 20, I believe. So we will use this again. So what this is telling me, it's 25% complete, which means 75% of my initial stuff is left. So I need to put a little thought into that as well. Right now. And so this is the right now part. So natural log 0.75 of the initial divided by the initial equals negative K times 42 minutes. That's the time right now. So these cancel, and so this is just the natural log of 75, natural log of 0.75, I should say, 0.75. The negatives cancel. And so I can do the negative 0.288 divided by 42. So 0.00686. And that would be inverse minutes for the unit. That's K. It's not asking for that. It's asking for the half-life. So we used this equation earlier, and we can convert that. To half-life by doing natural log of 2. 0.693 divided by 0.00686. And I got 101. And that would be minutes. Right there. All right, that's page 2. Number 12 shows me a mechanism. It asked me first to identify the intermediates included in the mechanism. So intermediates are things that are made in an early step and used up in a later step. So for example, I'm going to look at products of the early steps and see if they're an intermediate. So HOI is made here and it's used up here. So yes, cancels. That's an intermediate. OH is made here and it's used up here. Yep, that's an intermediate as well. H2O is made here. It's not used up. It's actually a product, so that stays. I2 is a product, H2O. So if everything else is a reactant or a product, which it is, then that's it. HOI and OH minus. For the rate of the reaction, I just look to the slow step only, and I write the rate. Rate equals K times the reactants, however many of them there are. So that's an elementary step. I can go straight to a rate from that. But as long as it's a slow step. So that's page 3. Now here's a kinetics problem where we're actually figuring out the rate law. Remember that we can always start with the generic rate law. Rate equals K times reactance, A and B in this one, raised to some powers. And what we're trying to do in the first part is figure out X and Y. So the order with respect to A, I'm going to pick which ones I want to plug in. Let's see, I want A to change and B not to change. It looks like 2 and 1 would be good. I'm just leaving the units off as I go, but I'm just doing number 2 first since it had the bigger rate. And K, A, B, and then number 1. Cancel out the K's, divide. That looks like 3. That looks like 3. So the power that would get me that answer would be 1. 3 to the 1 equals 3. Okay. So I know that, and I can just take that exponent out then because you don't have to write the exponent of 1. All right, now I want to do the same thing for B. I'm looking for a place where B changed, but A didn't, and it looks like I need to pick 2 and 4. So I've got 0.2, yeah. And actually, I don't even have to do anything for this one. I could do the same thing, but when I look to see if I want to write it with the bigger rate on top, and I see they're the same, that means when I change the concentration of B, nothing happens. So that's 0. Right? So if it doesn't change. So if I had gone through all of this, what I would have gotten is 1 equals 2 to the y, and to get any number to equal 1, I'd have to raise it to the 0th power. So either way, I could do it. The overall order is just x plus y, which is 1. The rate law is going back up here and plugging everything in. Now, since this is to the 0th power, it's going to just be gone. So that's just rate equals K times A. And now it asked me to figure out K, solve for K using including units. So I'm just going to use my rate law, solve for K. Sorry, there we go. And then I'm just going to pick an experiment and plug in the numbers. So I can't show you both parts at the same time. I'm just going to pick experiment 1. I want the rate on top. It's 7.25. Now the units look kind of crazy. Let me just write this out. It says moles over liters minutes. So moles per liter, that's molarity. So that's what they're trying to say. And then for the concentration, it's 0.125, and it says moles over liters, so that's also molarity. So I see the molarities cancel. My answer will be an inverse. Usually it's an inverse seconds for a first order reaction. It will be an inverse minutes this time, which is totally fine as long as it's a time unit. Actually, I'm looking at the answer key as I go, and that is wrong on the answer key. So let me make a note to myself to fix that, but it should be inverse minutes, not seconds. And that's it for page 4. All right, Le Chatelier's principle. So I've got a mixture of gases up here, and it says, you know, what will happen when I do all of these different things. So let me just take note of a couple of things. I've got nitrogen and oxygen on the left, NO on the right. I have 2 moles of gas on the left, and I have 2 moles of gas on the right. So that means anything related to pressure or volume will have no effect. And then also I'll just go ahead and cheat and look ahead a little bit here and see what my delta H is. It's positive, so that means it's endothermic. So I'm going to write heat in right now on the reactant side since it's an endothermic reaction. All right, so let's see what we got. Helium is added to increase the pressure of the system. No effect, right? And the no effect is because they have the same number of moles of gas on each side. The reaction mixture is heated, all right, and we already wrote where heat should go, so I increase the reactants. I'm going to shift to the products. NO is removed from the system as it's produced. So if I can remove NO, I'm going to need to make more of it. Shift to the right. If NO is added to the system, now I have too much products. That would be a shift back to the left. If the volume of the container is cut in half, that would shift to the side with less gas, which doesn't happen here, so no effect or no change. And if O2 is added to the system, that's a reactant. That would be a shift to the right. When something like helium, NO, NO, O2, when these things are added, if they're a reactant or product, then they're a reactant or they're product. They're a product. If there's something that you don't see as a reactant or product, then it's probably to affect the pressure. So just look for it to be a reactant or product first, like O2. All right. Here's a kinetics problem where we're looking for the rate of change of one thing with respect to the rate of change of something else. So I don't know why it's so blurry. Sorry, let me see if I can. There we go. Halfway through the exam and I finally figure out that it's out of focus. Sorry about that. All right, so I can write my rate with respect to all these different things, but I only care about two of them. So let me just write it with respect to that and that. So remember, if it's getting used up, it's a negative. 1 over the stoichiometric coefficient, which is just a 1 here, times the, usually it's the concentration here, it's the P, the partial pressure, but that's fine. Partial pressure of the H14, it's this whole thing. That's equal to, okay, so this is a product, so it's a positive. 1 over the stoichiometric coefficient, so 1 over 4. Change in, pressure, partial pressure of H2 over delta T. So remember, that's concentration, molarity. And this is partial pressure. And they're not the same thing, right? They're not the same, but they're both concentration units. If you have a gas, they're both ways of expressing how much gas you have, and it doesn't really matter which one I use as long as I'm consistent. So in this one, they're talking about partial pressures, and a lot of them we do molarity, so that's kind of what my hand defaults to, which is why I'm trying to write brackets, and it got kind of messy here and changed the bracket to a P. But it's just the amount, how the concentration changes over time. And it could be any concentration. It doesn't even have to be limited to these. Those are just the ones that we often see in our book. So regardless. All right, so then we just want to solve for that because that looks like that. And that says I should take that, which I was given. All right, there we go. Multiply it by negative, and then I got to get the 4 over there. So let me just write this out a little neater. Negative 4 times this. So that's the negative from there. Multiply by 4 to get this by itself, and then that's that. Okay. And then negative 4, and then negative this. And you can see now the negative and negative cancels, and I'll put it in my calculator. It's just going to be 6.2 times 10 to the minus 3 times 4. Let's see, 2 sig figs. On the answer key, I have it in scientific notation, but it doesn't matter. 0.025. The units would be atmospheres per second. Whoop, there we go. All right, europium, lanthanide, television screens, crystallizes body center, cubic, edge length. What's the density? Okay, so for density, remember we're doing mass divided by volume, but it's of a unit cell. For the mass, we're going to start with the molar mass from the periodic table. So I'm looking up europium here as 152. Grams per mole, and I'm going to convert that to grams per unit cell using Avogadro's number. be really careful when you write out the molar mass. That's grams on top, moles on the bottom, and that will help you get your Avogadro's number set up correctly, which is on your equation sheet here. It just says per mole because it could be anything per mole. In this case, it's atoms. But I don't want the moles to be on the bottom. I want the 1 mole to be on top, and I want to divide by Avogadro's number because that will give me grams per atom. And then I need the body-centered cubic. That's the 2 atoms per unit cell. That'll give me my mass of a unit cell. So 152 times 2 divided by 6.022 times 10 to the 23rd. 5.048 times 10 to the minus 22 grams per unit cell. All right, so that's my mass. Now I need to do the density. For the density, okay, I've got sorry, I'm reading this again. All right, edge length. Okay, so it could give me the radius. I'm looking at the equation sheet. That's why I paused there. I was looking at the radius here. I told you don't need to know the relationship between the radius and the edge length. It's not on the equation sheet. So if it did give you the radius, then in the problem I would also like tell you that relationship. But this one, it already gives me the edge length. Remember, we're talking about the volume of a cube, and it's telling me this is 240.6 picometers, and so I just cube it. Right, that's all I have to do. Now, if you remember, it needs to be in centimeters cubed. It doesn't really say in this one. On the exam, I'll try to be really specific about when I want specific units. In this one, I would want centimeters cubed. And so I like to convert it before I cube it, so I'm going to do that now. And that should give me 240. Let me just do this so you can see what I'm typing in case you're having trouble putting anything into your calculator. You might not be able to see the whole screen, but 240, I can fix that, I guess. There we go. 240.6 times 100 divided by 1 times 10 to the 12th. So I'm using that E button. And you can see it doesn't give me a lot of information. I mean, I can count all those, but I'm probably just going to do, for mine, it's second and then scientific. Oh, there we go. Instead of floating decimal, I want scientific notation. And so then that'd be the 2.406 times 10 to the minus 8. And it would be centimeters. And then that is what I can cube. And for that, I can just, once I have this in my calculator, and a lot of your calculators work the same way, I can just do that and it will put the answer cubed. 1.39 times 10 to the minus 23. All right, and then that's it. I've got my mass, I've got my volume, I just divide them. And let me just type this in all again so you can see it one more time in case you're struggling with that part of it. 5.048 times 10 to the minus 22 divided by 1.39 times 10 to the minus 23. This time I got times 10 to the 1. That's kind of a small number for scientific notation, so I'll go ahead and convert it back, and I got 36.3 grams per centimeter cubed. Man, we've done a lot already this semester. We're flying through all sorts of concepts, right? I'm sure I don't have to tell you that. You probably are feeling the amount of material. We'll slow down a little bit after this exam, I promise. All right, a solution contains 5 grams of propyl alcohol dissolved in enough water to make 450 milliliters of solution. What is the molarity? Molarity is moles of solute divided by liters of solution. I have 5 grams of my solute. I need it in moles, so I'm going to need the molar mass. use your periodic table for this. I happen to know the molar masses of all these things since that's part of my job. So I've got 3 carbons, which is 12. I've got 8 total hydrogen, 7 plus 1, and then oxygen is 16, so 60 grams per mole. All right, so 0.833. So the molarity would be 0.83, 0.0, there we go, 833 moles. And then I have a total of 450 milliliters of solution. Molarity is very specific that I need liters, so 0.450 liters. All right, what is the osmotic pressure of the solution? Don't forget about that I. In this case, I don't need it. How do I know I don't need it? I don't have a metal. So it's not an ionic compound. There's no metal in here, so I don't need to worry about it. I is just 1. But don't forget to think about it in case you do need it. The molarity is my 0.185. I'm going to write the molarity out as moles per liter just so I can look at my units really carefully. I want an answer in a pressure unit, so I'm going to choose my R that is in atmospheres here, so 0.0821. Liters and atmospheres on top, moles and Kelvin on the bottom. And then my temperature was 50 degrees Celsius. So I need to convert that to Kelvin. And I'll put this in my calculator. Let's see, I need about 3 sig figs, looks like would be good, 4.91 atmospheres. The only thing that didn't cancel, so moles, liters, Kelvin, and so my pressure would be in atmospheres. All right, write an expression for the equilibrium constants. All right, so the things to remember for equilibrium constant are products on top, reactants on the bottom. Stoichiometric coefficients become powers. Solids and liquids do not get included. Okay, I don't have any pure liquids here. So everything, gases and aqueous do. So that's it. Not much to remember as long as you remember those specific things. And there we go. All right, so this one, it's giving me a Kc, and all they want me to do is convert it to a Kp. So I just need an equation, Kp equals Kc times RT to the change in N power. I forgot to put that on the equation sheet. So if this is on your exam, I would include that equation written into the problem because I think I always get these mixed up, which one goes where. But anyway, this is the equation. So starting from the equation, could you finish the problem? All right, so what do I have? I'm looking for Kp. Kc was given to me. R and T are what go in here. Now, my T needs to be in Kelvin, so 900 plus 273 would be 1173 Kelvin. And this one's not so obvious what I want my unit to be, which one I should choose, but this is, Kc is in like moles and liters, right? Molarity stuff, and this is in atmospheres stuff. There's no energy in here, so I want to use the one with the moles and the liters and the atmospheres, not the other one. So the 0.0821 is the correct one. Not a lot of units to help me cancel, so I'm not going to worry about writing all that. All right, and then the last thing I need is the delta N, the change in N, which is the change in the number of moles of gas. Remember, delta means products minus reactants, so how many moles of gas in the product? That's 2, minus how many moles of gas in the reactant? That's just 1, so 2 minus 1 is 1, so just to the first power. So just multiply across. And I get 7.99. I should only have like 2 sig figs here, so I'll just round that to 8.0. All right, and oh, last one. Okay, number 20. So this is enthalpy, entropy, delta G, Gibbs free energy, K, all sorts of fun things in here. All right, so delta H, delta S, and I could do for delta G just products minus reactants. So I'm just going to go ahead and plug those in, and I'll fast forward this part of the video. Okay, so by the way, if you were watching when I put these in my calculator, I just distribute the negatives. So I put this in as a positive and this one in as a negative, so I could do it all in one go. You could also put it in with parentheses if you were confused what I was doing or why I had my signs wrong. That's what I was doing. As long as you know a way to get the right answer and you're comfortable with it, you're good to go. So these are the answers that I got. There is a question here that says, is it spontaneous? And it is a negative. So yes, it is spontaneous. Remember, if delta G is negative. Okay, I have 2 more things that I need to do here. One is to calculate K. There is a relationship here between K and delta G, and that is on my equation sheet, so I can use this. The way it's written is if I have the K and I'm solving for delta G, but I can go ahead either memorize the other way or convert it from here, whatever you want to do. I need to get the natural log by itself first, so divide by negative RT. And so that gives me natural log of K equals negative delta G standard over RT. And then to undo the natural log, I do the exponential function. So K equals the exponential of negative delta G over RT. And so then that would be the delta G that I got. Now the only thing I need to make sure is that the delta G and the R have the same unit. I'll just leave the delta G alone. Okay, so it's a negative, and then this was a negative. I got to be careful here. The equation has a negative, and my delta G has a negative, so that's actually a positive, 35.1 kilojoules per mole. And then my R is the 8.314, but I want it to be also in kilojoules, so 0.008314. And I'm at 298 Kelvin. All right, so all that goes in. You could do this lots of different ways in your calculator. Maybe I'll just do the exponent first. So 35.1 divided by 0.008314. I like to just hit enter and then do the other part of what I'm dividing by. So it's all in the denominator for sure. And then the E for that, of that. So exponential function of my answer is that. All right, that's a pretty huge number. I don't want that many sig figs, so I'll just convert it to scientific notation. I get 1.42 times 10 to the 6th. That's my K. And then the last thing it asked me for is the delta G at a different temperature. So for that, I need to use delta H minus T delta S. I have all the numbers I'm going to need here. So the delta H is negative 42.55. I know it's off screen, but that's from my part A. The temperature is 398 Kelvin that they just gave me. And then the S is my negative 22.19, but remember that's in joules. And so just anything like this, just be really aware of the units, making sure that the units will cancel. So I want the units to cancel here, so I'm going to leave them in kilojoules. So I'm going to convert this S to kilojoules. This is a negative from the equation, but there's a negative as well. So make sure I get that, 0.02216 kilojoules per mole Kelvin. All right, and I can put this in my calculator all together if I want, or in separate stages. I'm going to just do it together. Negative 42.55 minus, and then parentheses, 398 times negative 0.02216. Convert it back to floating decimal, and I get negative 33.7. And that's it. That's the practice exam. Good luck. Let me know if you have any questions. Where'd my mouse go? There we go.